I want to take a bit of a look at this idea of limits. Going to become important when we look at a more accurate way of finding the gradient function. So limits, how do we solve them? Well, the simplest way of doing it, if we can, is via direct substitution. So if I'm interested to know what our function's doing as the x value is approaching 5, I simply substitute it into the function and I get the answer 12. So I know as x is approaching 5, my function is getting closer to a value of 12, that distance above or below the x-axis. It doesn't always work. There's this idea, factorise and cancel. Now, if I had this one, x squared minus 9 on x minus 3, if I'm interested in what happens as x approaches 3, well, if I was to directly substitute into that one, I would get 0 over 0, which is a meaningless answer. So the first thing to do here is to factorise it, and we have the difference of 2 squares on the top, and then cancel the x minus 3. Now I've got something that I can directly substitute into, so 6. So I know as the x value is getting closer and closer to 3, our function is getting closer and closer to being 6 units, or above, in this case, the x-axis. I'm going to introduce a special limit here, and that's a limit as x approaches infinity. And it basically comes from our hyperbola, this starting point, because we know what this graph looks like. And we know as x approaches infinity, our graph, the height above the x-axis, is getting closer and closer to 0. So we use this limit as our basis. So if I have a situation where I've got like a polynomial and a polynomial, and I wanted to work out x approaches infinity, I want to rewrite this so that every time I'm substituting infinity in, it's the bottom of the fraction of each term. Now to do that, I would divide every term by the highest power, in this case x cubed. Because when I tidy that up, I now have a whole heap of fractions where I'm going to substitute infinity into the bottom of the fraction. Now by our special limit, we know each one of those fractions will become 0. So I end up with an answer of 1/4 for my limit. Now there's a quick way of doing that, because essentially what will happen is we will just be left with the coefficients of the highest power. So if I want to go into this one, the highest power again is x cubed, so I know the answer will be 0, because there is no x cubed term on top, over 1, and that is of course 0. This one here, highest power is 7, so I would be left with coefficient of x to the power of 7, which is 1 on the top and 3 on the bottom. So that would be approaching a third. X cubed is the highest one again. I'd end up with 1 on 0. 1 on 0, well, I've said there it equals infinity. It doesn't actually equal infinity, but what that's telling me is my curve is approaching infinity. So the y value, or the height of the curve above the x-axis in this case, is getting very big. It gives us another way of finding horizontal asymptotes. So this particular graph here. If the highest power is the same on the top and the bottom of the fraction, then I can use a limit to find the horizontal asymptote. This one will be 1 on 1, which is just 1. It will have a horizontal asymptote of y equals 1. All right, now our textbook doesn't actually have questions on this, so I've taken the exercise. It's in your handout from Terry Lee, so exercise 6.1.